adaptation. Hold on. We've been here before. Well, yes, to an extent, and we're going to go into it a little deeper. In this lecture, we are going to be covering adaptation and natural selection, but more importantly, we're going to be getting into calculating your own selection gradients and beginning to test hypotheses of adaptation. One should be able to define selection. Predict what will happen to Hardy-Weinberg equilibrium under selection and how. Give examples of natural selection's influence on allele frequency and calculate S from variation and fitness. We've already started that in a previous lecture, but you are going to have an opportunity to do that in a Microsoft Excel sheet. So selection. Selection, remember, is going to be acting either natural, sexual, or artificial to make a genotype to make a population more adapted to the environment in which it is. Now, the natural selection is going to be acting on individuals, and that's important to remember. It acts on individuals, but the effects can be seen on the allele frequencies in the population. Acts on individuals, acts on phenotypes, but it has effects on the population and has effects on genotypes. So not all individuals are surviving at equal rates, and they are not all contributing equally to the gene pool. That's the very idea of what selection is. And here we have, of course, our generalized mouse example, where not all organisms are going to be surviving. So you start with 36, 48, and 16 individuals of the homozygous dominant, heterozygous, and homozygous recessive categories. What happens is a homozygous dominant has 100% survival. The heterozygote only has 2/3 survival, and the homozygous recessive only has half survival. So in the next round, you see a change in the allele frequencies, quite rapidly, in fact, over a single generation. It can be significant and it can be rapid. So selection tends to be quick, but it really depends on how much change is going on. So let's look at that change in allele frequency more specifically. So what we have here is relatively high survivorship of the homozygote dominant, or recessive, the homozygous recessive. There's still rapid change in allele frequency. I want you to look at these numbers where you have the B1, those heterozygote dominant. They always have 100%. That B1, B2, the heterozygote, you see how it can have either 90% up to 99%, and 99.8% even. So a high survivorship of the heterozygote. And even with a 80% survivorship of the homozygous recessive, you can still see that it's even that much survival leaves a very strong selection and leads to fixation of the allele within about 20 generations. So that's if the homozygous, think about how much it would be if the deleterious allele was on the homozygous recessive and caused a relatively rapid, 0% survival. Think how quickly that would make the allele go to fixation for the dominant. Selection gradients are the measure of how strong the natural selection is for a trait. So before we move to that, what I want to cover is this. So first off, selection is going to act as as you saw, depending on how strong it is really how fast it's going to move to fixation. So that's really what this graph is showing in a nutshell. But what I want to show in more than a nutshell is this this calculation here. So you have here, and I got to make sure I get it right. So you have here the population fitness. Population fitness is going to equal your p squared, W11, and that's your survival of the homozygous dominant, plus 2pq, W12. And that there is the survival of your heterozygote. And you can probably guess it's coming. Yep, that's right, a q squared with w, and it's wearing a tutu. And that's going to be your survival, of course, of your heterozygote, or homozygous recessive. So what we see here is that you're multiplying these survival categories in here, and that's what you could see by the percentage surviving. So given a known p squared, known 2pq, and a known q squared, and given known survivorships, you can calculate what the fitness of the overall population is. And the fitness of the overall population should change over time as these ones are eliminated or as these ones are eliminated, depending on the situation. And that's going to increase the goal here, if evolution had a goal, the goal would be to increase the population fitness. All right, let's look at an example here. This is the example of malaria during pregnancy. So we've heard of the example of malaria in sickle cell anemia before, but here is during pregnancy. So Plasmodium will invade the placenta during pregnancy, which causes complications and reduces fitness of the mother. The vascular endothelial growth factor receptor 1, VEGFR1, is released by fetal cells into the mother's circulation. So the natural selection here will be on the fetus. And this SS, which is short, and the heterozygote genotypes produce more VEGFR1 than the two longs homozygous phenotypes. So we would expect to see more VEGFR, meaning less Plasmodium. That's kind of what we'd expect to see, that there is going to be selection for the SS and SL genotypes. Let's look. So they actually did this during 2 seasons. One was when there was no malaria, because, drier season, and one was during when there was malaria. So they saw, let's see, does malaria affect the rate at which pregnancies go to term, or is it in Hardy-Weinberg equilibrium? Well, they looked at the frequency of the S allele and saw it was about 55.5, and the frequency of the L allele was 44.5, and they calculated the genotype frequencies from that. They then looked at infants that were born during the low malaria season of the SS, SL, and LL, and saw that they pretty much matched the Hardy-Weinberg equilibrium. And as you see, that's those red stars right there for the SS, SL, and LL. There's a little bit of a difference, but again, with more of the dominant allele and less of the recessive allele, you can see that there's more of the dominant genotype and less of the recessive genotype. Okay, so pretty much matched Hardy-Weinberg. However, surviving infants during the high malaria season, the ones that actually came to term, they did not match Hardy-Weinberg. They were actually more heterozygotes than would be expected, suggesting that the heterozygous phenotype is actually advantageous during this, and suggesting that during times of malaria, VEGFR1 is not in Hardy-Weinberg equilibrium, but is actually being under natural selection by malaria. So this VEGFR1 is under natural selection by malaria. And that's kind of how you would test this. Another way you can test it is by looking at selection gradients. And that is where I want you to grab an Excel spreadsheet. So this is going to be kind of tricky if you're online. If you're just watching this for review, just stop it now. We're not going to go anywhere else besides this. If you're online watching it for the first time, I want you to open the selection gradient worksheet. You should see 2 distinct field sites. And these are 2 field sites that I was studying back in, I don't know which one I'm going to put up there, honestly. But there are 2 different field sites, and you're looking at selection at the field site. So I want you to actually think, too, the fitness might be an artifact of the field site. So you're going to want to calculate average fitness for each site separately. So if I chose a high and a low site, you calculate fitness for the high site and fitness for the low site. Keep them separate, because that's the population. And remember that the fitness of the individual is compared to the population. So you'll calculate the average seed mass. That's one of these traits we're looking at. So average seed mass, we're expecting that the bigger the seeds, the more you're going to suffer being eaten. So we might expect that the higher seed mass will have lower fitness. And that could be true at one or the other field site. But what we want to do, after you've calculated the average for the fitness, calculate the average seed mass, calculate the standard deviation of the seed mass, and that can be done, so average is just calculate average, and then you select the seeds. Standard deviation is just this, and you select them, and then you're going to take each individual one, so like for F2, minus, and then you choose your whatever field this is in, so maybe SH. If this is in H4, you're going to put that dollar sign right there and divide it by, if this is in H5, that dollar sign will hold it constant. If you have questions about this, you just hit me up on Zoom, and I'm glad to go over it. Screen share, I got the whole thing, glad to help you. I'll be helping the people in class, and if we might need to Zoom the class too, we'll see how that works. But the standardized seed mass is like that. Standard fitness is going to be your seeds divided by the average. Divided by the average? Divided by the average. Oh, it's like minus the average in a previous lecture. Meh. Anyway, create a scatter plot for each site. If you don't know how to create a scatter plot, now's as good a time to learn. Remember, I'm here to teach you Excel. So if you have questions regarding Excel, hit me up on Zoom, hit me up at office hours, send me an email and just set up an appointment. I'm glad to help. This is what we're going to be doing in class, is kind of this exercise. I'm going to make them struggle a little bit more, but I do want to see you be able to get this. So there should be a worksheet that comes with it. Hopefully I remember to put it up by then. I'm doing this about a month in advance. So yeah, calculate those selection gradients, enjoy yourself, and review these objectives. And that's where we are today. That's our lecture. Enjoy.